All right, Anna. So here is the video for the material that I didn't record the other day. So the first thing is on Earth. On Earth, person standing on the surface of the Earth, there is a column of air, all right? Carbon dioxide, nitrogen, oxygen, methane, and a lot of other water vapor, a lot of other small amounts of gases that are above our head. And that goes all the way up to the stratosphere, all right, up to, miles above us. And that exerts about 14.7 pounds per square inch of pressure on us. Now, you and I don't feel it because there's an opposite equal force kind of pushing out on us. At the same time. So we have this force on us all the time. It's much easier to call it something else, 1 ATM or 1 atmosphere of pressure. It's also called a few other things like 760 millimeters of torr or 760 millimeters of mercury, pascals. There's a lot of other kilopascals. There's a lot of other terms used depending on if you're doing some physics, if you're doing some chemistry. But the main two that we here in the United States use is 14.7 pounds per square inch. But an easier one is this 1 atmosphere, because everybody pretty much on the surface of the Earth has the same amount of molecules above our head all the way through the stratosphere. But the interesting thing is that when you put the same person in water, all right, and they're about 33 feet from the surface, you now have a second atmosphere or another atmosphere of pressure on you because of this water exerting pressure on you at the same time this air is above the water. So in essence, you have 2 atmospheres of pressure on you. That's why if you go fairly deep down in the water, you wouldn't be able to do this on a free dive. You'd probably be scuba diving. You'd feel a lot of force on you. And it has to do with, there's only 33 feet there, but it has to do with the density of the water. So the water is more dense, the molecules are close together. Therefore, you only need to go down 33 feet to feel a second atmosphere of pressure on you at that depth. And then if you go another 33 feet, so 66 feet down, you'd have 3 atmospheres of pressure on you. So this is all related to density of air versus the density of water. Now, the one thing about air is that we can easily compress air. So here's a can, right? So in a factory, if they were to fill up a can with some compressed gas, with some paint or whatever, they would force into the can, usually at the top, the molecules. And as the molecules are bumping around each other, right, there's a lot of heat given off. All right. So there's a lot of heat given off because the molecules are bumping into each other. They're bumping into the sides of the can. And all of that friction is creating a lot of heat. All right. And that heat has to always go from hot to cold. So if the can is hot, then it's going to go out into the factory somewhere. So on a manufacturing line where you're making something where you're compressing a lot of gas, you're going to eventually create a lot of heat while you do that. And just like heat goes from hot to cold, pressure also goes from high to low. So there's low pressure out here now, and there's high pressure inside of this can. And that's the whole idea behind trying to get this high pressure of material, usually liquid at the bottom. We're trying to get liquid at the bottom here that eventually cools as a gas. And as it cools, it condenses into a liquid at the bottom. So the molecules get closer together. If they get close enough, they form a liquid. So most cans have a certain amount of gas and a certain amount of liquid in it. Because of those molecules being under such high pressure, the molecules are being forced together. So if you think about inside this can, you have the pressure from all around it trying to push these molecules together as a gas. And if they get close enough, then they're going to turn into So if we think about this as being the distance between a gas, if you can get them close enough, maybe we can turn them into a liquid. But once you get them into a liquid, pressure really doesn't affect molecules as much as temperature does. So pressure, very important for the gases, especially when you're in a factory and trying to put those gases inside the can. So now what happens? You have this very high pressure inside the can. You have all these particles in there. So let me put a couple of particles in there. And you have, and I probably have a few more down at the bottom because they're liquid if you were to shake a can. And you have this low pressure outside the can. Well, just like heat wants to go from hot to cold, pressure wants to go from high to low. And in this case, we have a little button at the top. And if you push down on that button, all these molecules are going to come out here. And when it does, just like the heat over here is being created, the sides of the can, as this is happening, they're going to feel cool to your touch, right? This is going to feel cool. Why? Because these molecules, that many of them are liquid, they want to go out here because of the high pressure, but they also need something from our hand. They need something from the air around us. They need the energy to go from a liquid into a gas in this low pressure environment. So it takes the heat from the air that's on the outside of this can, as well as your hand that is actually on the can. So if you open up and release the pressure for quite a long time, you'll actually feel the side of a can getting colder. Just like in a factory, that can would be very hot as they're putting those molecules in from the low outside environment now into a high pressure inside that can. So energy is very important here because those liquid molecules want to become a gas. That gas needs a little bit of energy in addition to this low pressure to create this gas that's coming out of the can. And the other thing that we did the other day was a little demonstration. And the demonstration, what I'm going to do is just draw a little picture of it. So on a hot plate, all right? So on a hot plate, I put a can. And the can had, all right, the can had a little opening at the top. Okay? And I put some water in it. And as I was heating, the gases, the water would turn into water vapor and they would leave. Right? So you have all of these molecules in here very warm, and the very warm molecules are farther apart than they would normally be because it's on a hot plate. And then I had a bowl of water, and this bowl of water had, I would say, even some ice water. So I was heating the water over here. The high pressure inside was allowed to escape because there was a little hole there. And what I did was I took this can and I quickly turned it upside down, right? Turned it upside down now. And that hole is now covered with water. So the can cooled very quickly. And when it did, the outside pressure was trying to get inside because now this is low pressure in here. Why is it low pressure? Because you had all of these molecules that were and wanting to get out as I was heating it up. Well, these molecules now went very close together. And when they went very close together, there was a low pressure created because those molecules weren't moving around as quick anymore. So now there was low pressure inside the can and high pressure outside the can, even though it was just normal pressure that we would have in a classroom. But what it did was it bent this can and it pretty much crushed the can when this happened. So I'm going to share a video with you of this demonstration done by somebody else, and you're going to see what happens when you take some warm molecules moving around here, turn it very quickly upside down. Water actually gets forced into that little opening too, so water actually fills up this can after, or pretty much immediately after the can gets crushed. So a couple of things are going to happen there. So I hope that helps. I'm sorry that the video didn't work. I'll make sure that in the future that works. All right, let me know if you